Welcome. This is a session we're going to be talking about file systems and new enhancements that you have to your file system. If you are a storage administrator that looks after storage inside your environment, put up your hand right now. Now, of the people that have their hands up, how many of you also look after the SAN software and look after managing all the drives and the disks and everything else? If you're storage administrators, that's what you do. Keep your hands up, of course. Okay, all the rest of you who don't have a SAN administrator in the room, do you have a SAN? You do have a SAN, okay. Well, you don't need a SAN anymore. I'm just, not to put the storage administrators at, I got this unruly kind of sound started to appear in the room if you didn't hear that in the recording. What I'm trying to say is that we're bringing, how about this? We're bringing SAN-like technology to the masses, including workstations, for the stuff that you can do with SAN. And you don't need to have a degree in the black arts to understand how to use the SAN software. It's now available to be done in a much simpler form with some of the stuff that we're doing with storage spaces. Now, I started this off, if you were in my session about Active Directory, please don't answer this question. For people that were not in my session about Active Directory, can you see something wrong with this slide? What is wrong with this slide? There must be something. The biggest problem with this slide when I got this template, and I'm surprised it slipped through the legal department, is that you guys are missing this for the All Blacks. So that's the main place you want to do. Pardon me? No, the Microsoft logo is still good. You guys are thinking of the new logo. That's just the text. So that's just all the text is. And someone else asked me in the room, is there maple syrup? And yes, there is. There are 2 maple syrups up here for good questions. Again, I met someone at the social event on the first night that said that they still had the maple syrup they got in one of my sessions last year. So I told them, come to my sessions and you have a chance to win another one. So it's there. And also the other thing I said in my Active Directory session, which I'm not going to cover right now, it is not stolen maple syrup. There was in the news a theft of 30 million liters of maple syrup in Canada from the 160 million liter reserve of maple syrup that Canada maintains to make sure that the syrup prices of the world stay in balance. And I thought it was rather funny that they would have something like that in Canada, whereas in the States they have like the oil reserve to keep like the price of oil in balance. But then a friend of mine actually told me that there was a bacon incident in the States and that there is a very large theft of bacon. So I think, honestly, we have a bunch of hungry thieves is what it is, or else someone doesn't get breakfast in the morning. So we are going to be talking about file systems, which are nothing to do with maple syrup, bacon, or oil reserves. And this session was put together by the product team that looks after storage. If I had to think on just in an elevator conversation with someone, and they said, hey, Rick, what do you think is the biggest changes that have happened inside Windows Server 2012? The first thing I would say, virtualization, Hyper-V, all the stuff that you can do with Hyper-V inside virtualization. The second thing that I would say, storage. Storage is massively updated, revised, and significantly improved. Again, these are one of those technologies that kind of cuts across the swath of all the underlying technologies because storage is ubiquitous. It's in everything that you need on a server, and there's different ways you can do things. It goes way beyond the old days of FAT and FAT32, even beyond the days of NTFS, the stuff you can do now. And there are going to be some trade-offs. And so I'm going to start kind of slow to be able to talk about architecturally what the major changes are. First of all, talking about the abstraction layer, which is known as storage groups. That's basically where I'm going to be starting off and talking about storage groups. And then I'll be delving into some more stuff with what's known as the Resilient File System, or ReFS. And before you all go out and decide to reformat your drives with ReFS, I give you props for wanting to. Just hang on for a minute because there are some things that it does not support. There are some concerns you might want to have with it. So you'll be able to hear about all of those things that are coming up right now. But as I mentioned, it's such a big area of change that happened in storage. The area of change that happened an awful lot in is with regards to storage space. So I'm going to start off there. And so first off, this is a little bit of a marketing kind of discussion. The concept of where the storage actually hits home for individuals and offices and companies of all sizes. It doesn't matter if you're a small business, if you're a medium-sized or an enterprise medium-sized business, or even extra large. If you have a SAN, if you don't have a SAN. The stuff that you can do with storage spaces is just phenomenal for what it can do. It's primarily able to target systems that do not have a SAN architecture. That doesn't mean the people that work with SAN and SAN technologies and understand the ability to go off into great big, huge, massive sets of drives with RAID 10 and allocating different LUNs and that sort of stuff out to different people and VLANs and all sort of fun stuff like that. It doesn't mean all that goes to waste. That's all still available, still applicable, and definitely still in use. But I'm going to tell you that I can show you how to do stuff with a simple JBOD device tray of 60 drives plugged into the back of one of your servers to get similar technologies to what you're able to do with a $50,000 to $100,000 to $200,000 SAN, kind of some of these technologies. And it's built in the box. And it also applies equally between client as well as server. So basically, the two things I'm going to be covering today are storage spaces. The second thing, as I mentioned, is the resilient file system, or ReFS, for where it goes. Now, technically that means that, yes, you can save on your CapEx for capital expenditures if that's important to you. The main thing I look at it for is simply maximizing your availability because, as I used to say, Active Directory is like the dial tone service that has to be there all the time for you to be able to do anything on your servers. Well, Active Directory would be dead in the water if it didn't have a disk to sit its DIT file on to be able to do anything, right? So let's get those disk files up and working in the best way. So first off, the whole concept with storage and stuff that we're doing here, I'm looking primarily at talking about taking your block access or looking at file access for your individual systems. With SMB3, just to kind of jump ahead a little bit to the file level access level stuff, you can literally have a highly available file share, however that's being served up to your end users over the network. And then you now have application servers that can consume that file share and use it for its primary storage, like virtualization workloads. Hyper-V, VHDX, and VHD files can sit on top of SMB file storage. How that's served up is where Spaces comes into play, because it can be served up on one of these highly available file server clusters that can scale out and scale up on demand. But this also directly applies to block level access, where you have disks and app servers directly attached in with shared storage, SAS storage, onto a bunch of JBODs. Now, I went and talked to the HP/Intel guys when I first came here for the Expo Day before it opened. And they do have a couple of Server 2012 boxes that are up and running in there, but they didn't have any JBODs. First of all, do you know what JBOD stands for? Just a bunch of disks. Yes, in case you don't know. I'm going to be using acronyms an awful lot. So JBODs literally is simply a tray of drives that are slotted inside the tray of drives, let's say. Sometimes it's even integrated inside the same chassis as your server. But then it has network connectivity in the back that then plugs into some kind of a networking switch, and then, or maybe JBOD interfaces. That allows you to then go and plug it into the back of your servers. That's the kind of storage we're talking about as far as the more cost-efficient way of being able to have access to stuff. The downside of the JBODs in the past was the fact that there's no intelligence behind them. It literally is simply just a bunch of disks that are plugged in through a network connection into your system. Where I'm not talking iSCSI connectivity across the network to be able to get into these. Those require some level of an OS that serves it up, even if it's firmware or if it's another OS that's running, attaches into those guys. I'm talking literally of simply a tray of drives plugged into to the network with the proper connections that your servers can have access to. So it can do block level access directly down to the local drive, so the attached drive, if you will, of the SAS server, of the SAS connection into the JBODs, or it can be through a file share that's served up with one of these highly available file servers that's doing stuff. So that's some really new, interesting deployment methods that now exist, and deployment models that exist with what we're doing with storage. Traditionally, you would have your FIDO channel or your iSCSI or other connectivity into your big SAN array and big controllers, that sort of stuff. And you could also still have block access, or you can have file access into those. We're talking about the easier and lighter side. Now, when I say that it is the most cost-effective platform and easiest to be able to set up, is continuously available and highly scalable, what I'm talking about is this implementation of things called storage spaces. And so storage spaces really is the game changer that we've been introduced with this, for this individual storage. Now, I'm going to be demonstrating how to make a storage space after I explain all the architectural background for how it works and what you can do with it. And I'm going to be obviously doing it on a very simplistic system. I'm going to be using literally just a virtualized instance of a machine with some virtualized instance of disk, and then making a storage space off of that. But you'd be doing basically the same steps if you're using a SAS-connected drive enclosure to be able to do stuff. So storage space is your ability to go off and have a new category of capable storage that has lower price points, because you don't have all the extra hardware that's involved to be able to have a full-fledged SAN infrastructure that's out there. potentially lower price points, and then also simplified administration. You can actually manage storage spaces if they are direct attached, if they are through a SAS connection, if they're over top of the network, the exact same way, using the same interfaces built in, and that interface is Server Manager or PowerShell, and it's the exact same commands to be able to go off and to manage them if they're locally attached or if they're over the network that's out there. So the thing here is, again, bringing this cost-effective storage up to a new level of making it more mission critical and being able to serve up more throughput, being able to have more capabilities with what you can do with it. So you basically break this down into this concept of abstractions. And these abstractions are going to be in the form of storage pools. You have to basically create a storage pool of these drives. So if you have a tray of 60 drives, you carve that up into a single storage pool, or multiple storage pools if you want, for different reasons. It's simply a unit of aggregation that you then will build on top of once you've gone ahead and grouped these systems. It also is a way you can go off and delegate out administration if you wanted to make it so that other people can go off and manage their own storage once you've allocated them some space on your system. It also is a way of doing some isolation. If you have different speeds of drives, different groupings of drives, if you wanted to, you can go off and make a different pool that matches up to your architecture that's out there. Therefore, you can optimize the traffic, you can control who has access to it, and other things like that. For all the people that are storage administrators now with SANs and with SAN architecture and different things, you're probably saying, yeah, so what? I've been doing this for years. And the answer is yes, you have been doing this for years. So this is simply bringing it down to a level where it's not involved in the SAN architecture. Now, the storage spaces you layer on top of this, and the storage space basically is what gives you the ability to have resiliency on these drives, to be able to set up a way of having mirrored spaces, having parity spaces, or having simply striped spaces across of them. And the neat thing is you can have different types of spaces inside a single pool of disk based on what it's serving up and what makes the most important access to it. It also allows you to easily provision them and also allows you to basically tweak and tune for performance. Now, this is using, as far as a direct connection into your server, these devices can be set up and be used with a SAS drive directly onto the box, onto the box with interconnect. It can also be USB. Again, this works at a workstation level as well. You could have multiple USB 3 enclosures that are on the back of your high-end workstation for video editing, and you can set up SAN-like capabilities on those drive enclosures if you wanted to. It also could be just directly SATA drives that are plugged into the system as well. So if you're looking at this from a, again, very small business, small, medium business, you've got a lot of choice and a lot of cost price points that can go into this, even for your own home hobbyist environment too, and have all the same capabilities. But then obviously when you start going to larger end things, you're going to be talking about enclosures. And the neat thing is that the stuff that you build within storage spaces is enclosure aware and also driver aware, to be able to figure out the best place to put stuff to make it so it's more optimized. I mean, think about it. If I have a mirrored drive set, it makes more sense to have that mirrored set have one drive inside one enclosure and one drive inside the other enclosure in case one enclosure goes down, as opposed to having it side by side inside the same enclosure. So it understands your architecture, it abstracts it, but then it also is able to determine, based on what you're making, where to best put the data that you're going to be using. Very cool, very interesting where it goes. You guys already told me what a JBOD was, so I don't have to bother explaining that, so everything's all good. Now, from a storage spaces model, as I mentioned, architecturally, if we look at this, we have, going from the bottom up, basically a bunch of cost-effective disks that are there, regardless of their interface that they're using. They're simply plugged inside your different types of trays. This is an example of just a generic tray that has 60 drives inside of it that can be populated. And those are basically your SAS-connected JBOD arrays that are down below, plugged inside your rack. And then on top of that, of the physical disk, you then go in and you create your virtualized resilient storage, which is basically your spaces. And then as you can see, you can mix and match mirror spaces, parity spaces, and even just striped spaces across them. And they will choose the logical drives that makes the most sense, physical drives beneath them, sorry, that makes the most sense underneath it. And then above that, you have your server running that basically can go off and to use these. So basically, you've got your FSRM, file server resource manager utility to be able to go off and manage different things and aspects of it. You've got failover clustering that can take advantage of these if they're network connected. You've got, obviously, resilient file system, or ReFS, as well as NTFS as two different format options for your volumes on top of these different spaces. And then you have different connectivity mechanisms to get into these guys, either SMB3 or faster RDMA access. And then also you have a consistent experience for management across these different things, being either server manager or being PowerShell to go off and to manage them. And then lastly, you obviously have either physical or virtual systems that are connected up into these. You've got a wide range of different building blocks to be able to create your new storage architecture. You can take your existing stuff now and be able to use it, or this is also obviously applicable in a new greenfield install to be able to go off and to use this. This is obviously only available if you're running Server 2012. Do you know if this is available in the standard version of Server? Yes, it is. Is it available in the data center version of Server? Yes, it is. Did you know there's no difference between standard and data center except for the price point? And also the virtualization rights, obviously, and the method you procure it. But virtualization rights are slightly different for standard versus data center editions. This is the model that we're going to be going with and talking about. Example, you've got 360s, so you got basically 180 drives that can be carved up in any way you wanted to and then used with a variety of different types of capabilities. We didn't want it to be a limiting factor where you could only use certain capabilities within this. It simply is a transparent part of the OS that we're going to be using. That's in there. Now, physical deployment topologies, let's take a look at the simplest, where you have a single server talking to a tray of drives. That's the easiest way you can go off and be able to make this. It could be a 1U server as long as it has interconnects on the back. You've got a common switch between them, and then you've got a tray of drives down beneath it. Or architecturally, even if you have the drives inside the system itself, then you can just use the locally attached drives as well as one way of doing this. You can also go through and expand this off to be shared SAS, where you literally have, I don't know, a Mellanox switch, super fast with 54 gigabit connection between the server and the JBOD device, or you've got gig Ethernet, or you've got 10 gig Ethernet talking into your different switches to be able to talk to this individual chunk of drives. The important thing is that with shared SAS, all those servers have access to all those drives that you're making and have access to. So you can carve it up quite creatively. And it turns into a nice little building block that you can create. So to dive into what this is, to kind of give you the basic overview of the top-level architecture, we're going to look at the concept of how to carve this up for capacity, different reasons. We'll talk more about how the resiliency to drive failure has been introduced with this. This is where some of the things that you are used to doing with your existing SAN architecture comes into play. The way that you actually go off and manage and use these inside the real-world environment. Some concepts about high availability, how you can scale these in elastic form. And then finally, what you can do for some workload optimized performance. Now, first off, my father was a electrical engineer and got me involved in IT ages and ages ago. And one of the things that he told me still holds true today, which is basically no matter how large and how much data you can fit on that 5 1/4 floppy, you will fill it up. And that's when you simply took the 5 1/4 floppy and you flipped it over and you notched it and you used it again. And then you fill that up. And then you have to get another one, and another one, another one. So the same thing applies regardless of the size of the drive. It's always funny to see, we've reached the 2 terabyte, we've reached the 2.5, the 3, the more. Doesn't matter how many platters you can get spinning inside an enclosure, you will fill it. And the same thing applies if you have a massive array of all these disks that are inside your SAN environment or your JBODs. You will fill them up eventually in some way, shape, or form. So one of the big things that we made as far as storage spaces are concerned is the ability to go off and to, first of all, reclaim some space that is no longer required by your different applications. It's known as trim, or the ability to unmap with capacity reclamation. And the ability to go through and to elastically expand on that storage, to have more cloud-like capabilities to expand on that storage without having to redo your entire stripe set, redo your entire mirror set and that sort of stuff. And so through the ability of doing, in this case, capacity reclamation, think of it as a something that's like a easy way I can explain this is think of a dynamic disk that's able to grow and shrink with inside Hyper-V, as an example. If that's put on top of a volume that's part of a storage space, and that volume is being shared on a storage pool, where other volumes are also on that storage pool. If that particular guy grows and then shrinks back down again, the storage space is actually able to, at the operating system level, reclaim some of that space that was used and allocate it out to a different volume, if they're both set to grow. because you're able to make a fixed, or you're able to make one that's trimmed that can actually grow up. So basically, it can reclaim space, very important to know. It also is able to do that through a scheduled process as well, as opposed to on-demand with individual applications. And then from an elasticity perspective, it quite literally is, in this case, you might have 36 terabytes across 72 disks being independently used by 2 different companies, as an example. You have what's known as thinly provisioned storage spaces. The ability to thinly provision, you literally are taking your drives, grouping them together into a pool. You then make your storage space, and then you choose to make it into resilient or not. And then when you make your volume, you can say, do I really want to allocate the full size and make it fixed, or do I want to do a thin provision, where I'm going to say, you know what, how many do I got here? These 36 terabytes, really, I'm going to say it's, I don't know, 100 terabytes instead. And it will go ahead and say, okay, sure. So as far as the operating system is concerned and the users are concerned, it looks like 100 terabytes. But it actually only provisions the space that it needs, and then is able to grow up to a certain point. You will get alerts and monitors to the fact that that drive space is becoming low, and you will actually get a big hard warning when you reach that max that you need to have added more space before you got there to be able to fix it. It literally is as simple as going in, adding more storage into the same network accessible enclosure that you have, and then once those drives have spun up, you go into your manager program and simply say, add in more disk into this pool, and then more storage space physically becomes available. No changes, no offline time, anything else like that is now possible. So it is, again, relatively important to understand. You can dynamically expand upon this. Make sure you set realistic numbers. You know, obviously don't say that you've got an exabyte of storage that's out there, because I'm sure you're going to find someone that'll fill up that exabyte of storage space inside your environment. So be aware of that. Very easy to do. I'm going to be making a storage space that's going to be set up as a mirrored storage space. I'm going to do a thin provisioning of that to pretend that it's a terabyte in size, when in fact it's only 270 virtual disks, 170 gig virtual disks that are being installed. And you'll see just how easy it is to be able to mock it out and say it's actually a terabyte in storage. Now, it's resiliency to drive failure, this concept of having mirrored spaces and also having parity spaces that are in there. So you've got your drives that are out there, you make your pool, you then go in and you make your spaces on top of your pool. I can go off and choose to make a space that is going to be a mirrored space, or it's going to be a parity, and I have to physically select the disks that are being used, that are inside my system. The neat thing, as I mentioned earlier, is that the management interface and the smarts of storage spaces underneath it is smart enough to know that it should, if it has the option, it should move those drives that are being selected across different enclosures, if possible, to get you better resiliency when it's out there. And what happens is basically it uses this thing that's called dirty region tracking, and also, what's the other one that uses? Dirty region tracking, and now I'm blanking on that one there. Well, we'll go with the dirty region tracking. It goes and basically is able to track inside the parity space where there is bad stuff happening on the different physical layers of the disks, and will go off and move content out into different areas, and then map that drive as being bad, and possibly end up having to move it all together off of that spot. You are able to go on and to allocate drives in not only as automatic, where it is either used or not used, but instead can be set up as a hot spare. You can have multiple hot spares in there as you want to. The repair actions basically happen on that bad area when they're online. You don't have to worry about taking those drives offline to be able to go off and fix it. So it will go in and detect when that drive actually fails. If that drive held the parity bits or held the mirrored sectors and mirrored chunks of the data from other areas, it'll automatically spread that out onto the different systems as it needs to, based on the type of resiliency that you're asking for. Now, from an operational perspective, to simplify things, you're going to be using your storage management via PowerShell, or you're going to be using Server Manager to manage this inside your environment. As I mentioned, it is enclosure aware. It is able to go off and to, based on how you've set up your drives, how you set up your spaces, determine that certain drives should be allocated from this enclosure, certain drives from that enclosure, to give you the best protection. But it also is granular in the sense that if I wanted to, I could have one higher level admin on the box that's being and looking after all the stuff with regards to storage. to be able to go off and do the very first level of provisioning. But then I'm able to actually go ahead and create an environment where I have a tenant administrator that looks after a pool of disks that are there, and then that tenant administrator can choose to basically make the spaces and to define those spaces for the individual workloads, or I can have a workload administrator that basically just looks after one set of drives that are inside of a simple space. So you have 3 different levels of granularity you can get to, all using standard Active Directory as far as group memberships are concerned, and standard ACLs as well. And before anyone asks, if you're wondering if you can do this by using the Dynamic Access Control, or DAC, you cannot. It's only through groups and group memberships across the access control lists, in this case, for being able to set this up. So you do have granular control for where things go, all based on Active Directory authentication. Now, when I mentioned that you can choose the types of disks that are included in those different types of pools, the reason why you would do this is in case you're mixing solid state, very expensive high-end drives with very, very fast 15,000 RPM drives, with more commodity 7,200 RPM drives, or some really old clunker, very slow drives used for archival purposes. And you basically align your pools along these drives that you've set up to be able to have different performance systems. And so, for instance, here you got an example of having some solid-state drives that are set up as a one pool together, allocated into 2 different spaces, and then that one pool carved up into 2 different spaces are serving up, let's say, a CRM solution or a database solution that you're going to consider as your gold standard for your highest end costing of drives and storage space. You have a different one with 15,000 RPM disk being used for generic applications for everyday use, and then you got your very slower systems being used for your long-term storage. That's how you basically align and get this different level of segregation of your hardware investment to better optimize your access to your space. So that can be done, very simple to be able to do it. From a standalone server perspective, you basically have a low number of individual servers, each with directly attached storage that you're now making this up and having access to for your individual clients. You can have multiple spaces, you can have multiple drives based on your architecture, and it generally works in the sense that you will rely on the fact that the drives will fail. You'll have enough drives inside that enclosure that can basically kick in as a hot spare to be able to fix stuff on the fly and be able to still continue to work. And potentially you'll have periods of downtime for those workloads, which may or may not be acceptable to some people. This is your simplest implementation, easiest way to do it. Interesting thing about this, in case you're wondering, I'm surprised no one's asked me a question yet, but on a standalone system using storage spaces, it is a very minute penalty as far as performance is concerned for being able to abstract these disks away from the physical hardware that's out there. Negligible performance hits when you're using this. The important thing to note of this slide is the fact that it follows it right across the board. There's no hockey stick. There's no flat plateau as far as performance goes. It tracks all the way out to the largest implementations in our test beds. So you don't have to worry about this. Pardon me? Okay, good question. Basically, does this change if you're doing thin provisioning? Provided you don't exceed your drives and you drop off the edge of the earth, it continues like this and it's still just fine. It doesn't matter with thin provisioning. So in this case, you've got some 1 meg sequential, 1 meg 4K random writes, that sort of stuff, different types of tests and that sort of stuff to be able to do it. Again, you can try this with a Windows 8 client if you wanted to get used to understand how this works, or virtualize like I'm about to do here to see where it fits. Now, as a architect that used to design systems in my previous life, this gets really interesting when you step this up to the next level. And that's where you go away from a single server with a SAS disk to multiple servers with shared SAS disk to be able to have access to it. And what this means now is you have network connectivity to a batch of drives, and then you restrict or you enhance or you basically have the switching infrastructure to be able to have multiple endpoints into that batch of disk to be able to do some very, very creative things. And so now think about this where you basically have a clustered storage space deployment, where you now have 2 to 4 servers that are inside a rack that have networking connectivity down to the shared SAS storage. And basically all 2 to 4 of those servers have access to the same pool of disk and can now have access to it. You then are able to go off and set up a highly available workload of a file server, let's say. And once you have a highly available workload of a file server, you can serve up that disk protected with storage spaces, with, whatever file system you want on there, out to your application servers. SQL can use that shared storage via that file share that's now highly available. And if one of those servers goes down, your file share keeps on working. Because with SMB3, you can remap even open files to be able to do stuff. Same thing goes for virtualization. So extremely powerful. Does not require a SAN to do this. Simply a bunch of disks, networking connectivity with your JBODs, up to your storage. Obviously, you get what you pay for when you architect the solution. Don't just go with like a single 1 gig Ethernet per server into your JBOD. You might as well use ArcNet or something like that if you're going that route. But this now can become, as another thing to kind of blow your minds a bit more, this could become a new building block for how you decide to architect your systems. What happens if you start to get throughput issues? What happens if you start to get storage space issues? What do you have to do? This is the 3-node cluster. What do you have to do? Add another node. Add another node. How many nodes can you have in Hyper-V? How many nodes can you have in clustering in Windows Server 2012? 64 nodes across the board with all these different disks to be able to have access to stuff. That's how you can now move stuff around across those different workloads to be able to do stuff. So very, very cool from this perspective of now having scale with this continuous availability because these disks are now active. So this also becomes even cooler when you go to that next level of stuff. I wish I brought one, but I injured my arm, so I couldn't take extra luggage with me. And I was actually going to bring this new architecture, hardware architecture that I'm super psyched about, which is called cluster in a box. Cluster in a box literally is a 2U or a 4U, based on the manufacturer specs, system that is basically, don't think of it like 2 blades or 4 blades that has a back-end infrastructure. Think of it as literally 2 servers inside one chassis that has multiple interconnects into shared network accessible storage, all inside a 2U chassis. And you plug a next one into it, and then now both of those chunks of drives are accessible by all 4 of those. Another one, 3 of those chunks of drives are available to all 6 of those. And that's now a 2U server rack. So all the major manufacturers are out there planning on releasing this newer architecture form factor. You can use these as architects yourselves to design your own solutions. They're coming out for sure. I saw, touched, and felt the one that I was interested in, which is one of the first guys out of the gate, a company called Quanta. They have a phenomenal solution that's, again, in a 2U or 4U. Very, very sizable, stackable, and dynamically growable. Architecturally, how do you connect all this stuff together? Well, here you go. In this case, you've got some generic servers that are up there. They have a couple of cards that are able to attach up to the storage network. In this case, ideally, for this scenario, for 4 60-bay SAS network storage drives, you would have 2 connections from each card being able to go into, through different switches, into the storage network, and then the back of the JBOD device would be able to have multiple connections in there as well. So ideally, you would have 2 paths per server to get to each and every single one of these individual SAS drives that are through shared network to be able to have access to them across the board. Again, redundancy. This is getting pricey, just so you know. This isn't free, but this is what you could do architecturally. Very, very cool stuff for how you can do this. So in this case, the first situation, if you want to take a look at this from a total sheer size perspective, with 60 bays times 4, which is basically, looking at my cheat sheet here, if I had 3 terabyte disks, 60 of them inside each one of these guys, times 4 JBOD enclosures, you're looking at 720 terabytes of storage space inside this one environment of high capacity, high availability storage that's in there. If I instead decided to go a different route for going faster, potentially, I could go with 600 gig 15K drives. You're looking at 144 terabytes of storage space for mid-level performance. And then you could then finally go down to the creme de la creme, solid-state drives, 400 gig solid-state drives for 96 terabytes of extremely super high performance that's out there. What I could do with that. I'd love to have that. Unfortunately, I have a laptop to demo this on. Blowing this up one last level just to kind of talk about architecturally what you could do. Here's an example of one of the test units that are inside the Microsoft office down the road from where I'm at in Redmond. And they basically have created what they call their deployment element, which is that 2 to 4 servers. Actually, it's 4 servers that are inside your elements. So they're basically 4 2U servers, and they have multiple connects into the network drives. You've got 16 of these deployment units, giving you a total of 64 nodes. So basically, you got your 64 node cluster. And then you have a total number of disks, in this case, 242 hard disks and solid-state drives. You've got 4 40 Mellanox gigabit networks connections per server. And you've got 1 JBOD set up for each of those guys. Basically, what this all ends out to being is about 4 solidly packed racks for a 64-node cluster that has ultimate performance and ultimate testing to be able to do this. So very, very cool, the stuff you can do. And how do you manage this? What do? PowerShell or Server Manager. There's no extra software to learn. There's no craziness of other stuff to understand. You don't have to know anything about how to reinitialize an EMC enclosure and that sort of stuff. It's simply a matter of disks, plug them in, turn them on, and off you go. Question I have for you, it's kind of neat. How do you know which one of those drives fails? When you have that many drives. There's actually a thing I'll show you that you can turn on, and it will do something really cool, but I can't demo it. Well, I'll tell you. It's basically, you can actually go into the Server Manager interface or the PowerShell command, find the drive that's failed, right mouse click on the drive and say blink. And it will actually blink the light on the drive inside the enclosure, and you can find out which drive it is to be able to pull it out. So that must have been a very interesting feature request that had to go into play to get this done. A Morse code to be able to say this one stupid, this one stupid. I don't know if it's Morse code. It'd be a good one though. Good one. Okay, I'm going to quickly show you how to build a storage space. It's going to be nowhere near as impressive, unfortunately, as having a 64-node cluster of stuff to be able to show you this on. So I'm just going to show you the basic principles of how you do this. I'll be doing a whole session on Server Manager tomorrow. You should come out and take a look at it. It's going to be a lot of fun. But everything is done within Server Manager. Just go in here to your file services to be able to look at your volumes that are out there from individual servers. And as you can see here, I currently have, as it warms up, I have basically my C drive, and that's it. Nothing else. This is simply my system reserve partition, nothing else that's in there. And if I go down and take a look at it, I can see that it's a single disk, and basically that's about it with some shares that are on there as well. Not too much. If I go and take a look at individual disks, I have a bunch of different disks that are available. They're currently offline. Those are my mock SAS attached SCSI connection that's out there that I can do stuff, but I have nothing. I have no pools. I have no volumes or anything else. So what I'll do here is simply choose 2 of my physical disks, right mouse click on that and say new storage pool. You always start with a pool first and then build your way up. So you can read this, yada, yada, yada. Good link to have internet connectivity to check out more about pools. And you want to give this guy a name, demo disk pool. And I'm choosing 2 drives. I'm not going to bother, but I could add the 3rd guy in and make him into a hot spare. For this demo, I'm just going to leave it as a 2 guy set up as automatic for the type of thing I'm going to do. Total capacity at the bottom, as you can see, is 254. And it says, OK, it's all done. We're going to go ahead and make it. Go ahead and hit create. And there's a little link at the bottom here that says create a virtual disk when this wizard is finished. So I'm going to say, yes, please, go ahead, make a virtual disk. Next wizard kicks off. Virtual disk is a collection of 1 or more physical disks from a pool. So I'm going to check and create my pool. There it is there. It's created with an existing capacity of 253. And I'm going to call this one here my storage disks. And in this case, this is where you basically can go in and choose, I want to go in and make one as a mirror, and then if I had more drives, make some of them as parity, or make some of them as simple. I'm going to make this guy into a mirror set. Now, this is able to do both the traditional single disk failure with 2, or you can actually do multiple disk failure with 5, which is an improvement over the previous version. I'm just choosing 2. I'm going to choose thinly provisioned, and I'm going to say this is a 1 terabyte drive as far as the OS is concerned, even though it's not. So that's called thin provisioning. And then I say create. And now comes down to saying done, make a volume. Last wizard kicks off. I want to make a new volume. In this case, you can see here that I've got my server that's involved. This is my new virtualized disk exposed to the operating system. That's basically my storage space that's powering it right now. I'm going to say next. I'm going to make this guy 500 gigs. I'm going to call him drive letter N. And I'm going to say that he's going to be my NTFS volume. In case you can't tell, I'm setting up for my next demo. So I'm doing a 64K allocation size. I'm not going to bother generating short names, don't need them. Hit create. My N volume is created for me, and it's now done. If I go back and just refresh this now, I should see some more interesting information up here when it refreshes. And my demo disk pool that I allocated my drives from, I have one virtual disk that's created. It's called a mirror set, and it is a thin provision 1 terabyte drive. If I go back up here to individual disks, you can see here that I have still one available that can be used. The virtualized one is now showing up and visible inside my operating system. And inside I can see my volumes. I have one volume, thinly provisioned of 500 gigs. Neat thing about this is I can go ahead under volumes. There's my volumes, my actual space being used. I can go in and say do another volume for my ReFS setup. So that's my disk I want to curve up, 500 gigs. I'm going to call this guy O for other, and I'm choosing ReFS. Notice you didn't catch that. This little guy grays out, generate short file names. In case you don't know, short file names are not supported on ReFS, and I'll talk about that in just a minute. This is ReFS data. Hit next, create, and he's done. Close. Again, that would have been a lot easier through PowerShell to do. I'm doing it through a graphical interface. You guys can see it. This is basically where you're going to get your warnings in case you start to get too close to your actual thinly provisioned and physical size of your disks that are out there. You'll get alerts inside your server manager to say that there's issues and you should go off and fix them. Basically, I have now made a storage pool of a bunch of disk, and then inside that storage pool that I've grouped together inside my enclosures, if you will, I then have gone ahead and created a virtualized disk, and that's where the storage space comes into play to choose I want to make it into a parity or I want to make it into a mirrored set. And then finally, once that was made and abstracted by the operating system, I then simply layer on the traditional new volume, and choose the formatting of how that works. So now if I take a look at this inside the Explorer interface, pretty simple. There's my N drive, there's my O drive. That's it. Okay, I made a storage space. Woo, exciting. It could be bigger, it could be cooler, but that's basically as fast as I could do it for a demo to fit inside this environment. The big thing is, again, it works on a client, scalable all the way up to a server enterprise environment. It's the same steps for all those different drives that are out there. Now, storage spaces gives that new category of the lower price points, operational simplicity, yada, yada, yada. Let's talk about the cool new thing, which is this thing called ReFS, a resilient file system. The reason why I showed you storage spaces first is because resilient file system leverages the stuff inside a storage space to do some of its resiliency that's in there. It's important to note and understand how storage spaces work before we start talking about ReFS. Now, with ReFS, basically it is a brand new file system that is delivered demanding customers, sizing, innovations, basically NTFS, over 20 years of experience inside NTFS from where it comes from and where it is right now. And it's reached the point of time where it now needs to get a little bit more robust in what you can do. We've taken our learnings from the NTFS environment and then brought them inside ReFS. Is ReFS NTFS v2? No, it's not. It's a new file system, as you'll see from the way that it handles accessing files and working with files on the box. But we've taken our stuff that we've learned from NTFS and included inside of it. The things that we're looking at here basically are four main things. The first of the four is basically integrity. The concept here is that metadata corruption is always going to be detected by the write actions of the file system driver to see if there's any problems with the data that's on the drive. You can turn it on for the user data, but basically it's there for metadata and the actual file system itself. ReFS uses the resiliency capabilities of the storage space to be able to autocorrect stuff on the fly, which hopefully my demo will play nice with me, and I'll show you that in just a moment. Scalability, very, very cool stuff. Anyone know how big an NTFS volume can get to? Not exact numbers. I'm going to query Nathan to see if he remembers. You don't remember? Exabytes. Exabytes in size. ReFS, you know how big it can get? Beyond petabytes in size. Again, just from the sheer number of size of disks. I don't know how many disks are out there, but it's absolutely massive what it can do. And just be able to handle that, interesting thing is the number of files in a single directory. Here's one for you. How many individual files can you have inside a single directory within our ReFS? I'm going to read this out. 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709,551,616. Oh, minus 1, 615. That's how many files you can have inside a single directory that's out there. If you have that many files, how long do you think checkdist takes to run? That's a hint. Availability. ReFS maximizes data availability with how it can handle stuff and how it accesses stuff. I'll show you how that works. But basically, if a corruption occurs to an individual file and you've chosen to store that particular ReFS file system on top of a resilient storage space, like a mirror or a parity, you don't even notice because the file system automatically gets the good part of the file from the other drive. Doesn't happen with NTFS. You simply get blocked. Doesn't work. It's done. This actually does it on the fly. Very, very cool. And literally, this is an architectural evolution where it takes the stuff that it used and learned from NTFS and brings it up inside the ReFS world. So looking at this from an integrity perspective, basically, ReFS was designed from the perspective of understanding that integrity-wise, if you're going to be going off and modifying a file in the same spot where the file resides, you're going to end up possibly corrupting that file. And so it does allocate on write actions as opposed to in-place updates to be able to ensure that it's not going to damage the data that's on there, and then repurposes that space later on. Checksums are written to the data as well as the data itself to ensure that it can see if that data has changed on the platter for some reason since it was last written to be able, again, check for integrity for what's there. The file system metadata is always protected on that operating system, maximizing your ability to have access to it. User data protection is not on by default. You have to turn that on a per directory, per volume, and even a per file basis to make sure that it's protected in the same fashion. So those are your choices for where integrity goes. So how ReFS and storage spaces works together is one thing to understand. Basically, there is this process that runs on a scheduled basis called a scrubber, and that scrubber is going to go through both for NTFS partitions and also for data volumes that are ReFS, and then take a look and see if things are having problems. So with NTFS, if it detects a problem on a read of the data, because the user's initiating a read, it's going to go ahead and get the data from a good copy of the file. On ReFS, when it detects a problem, it's going to read the data, validate it against the checksum that was stored with that data, and then, if it's bad, go and get a copy from the good and fix the bad for next time. Very, very cool. So it corrects on the fly. There's an example of what it does for read attributes. There's an example of what it does with checksum data on the system. It does a verification of those checksums before it goes off as it reads it and autocorrects on the file. Very, very cool stuff for how that works. The neat thing about that, that's on a scheduled basis. The neat thing about that is on the fly. This is what NTFS can't do. NTFS basically on the fly, if it accesses the file and it's corrupted, it just is corrupted. You can't have access to it. Scrubber can fix it potentially, and then you're good to go. On this side of things, ReFS does it on the fly if there's a problem. ReFS detects the problem, automatically replaces that data with the good stuff, and then you're good to go. So here's my attempt. I still have 10 minutes, if I remember correctly. I'm looking at Nathan, but he's not paying attention. So I believe I still have 10 minutes left. I want to show you this demo. Bear with me to understand if I get these files and these commands right. Now, I have my N drive, which is NTFS, and my O drive, which is ReFS. Oh, yeah. I guess I'd probably do that, eh? Well, the demo would be perfect if you didn't see it. Okay. On your left, is this your left? Okay. On your left is going to be one side. On your right, it's going to be another. So on this guy here, we're going to go in and change to my C drive, change back out again, go into my ReFS data directory structure, and I'm going to say create file. This is a batch file that I've created that goes in and basically takes a good known picture, copies it onto NTFS. NTFS is which drive again? My N drive. I'm going to say create drive, and I'm going to say N:, It copies an image called image102.jpg. I'm going to start up my ever so nicely MS Paint. I'm going to say n:\images image 2. It's a picture I found of myself and my daughter taken about 5 years ago, and I don't have any other copies of this data, so it's pretty important. It's working on the NTFS drive. Over here, I'm going to do the exact same thing. Change over, go into my ReFS demo structure, create my file on my O drive. O drive is our EFS. I'm going to look at it. You can visually see the data is basically the same on both of those systems, if you can read hex, right? Trust me, it's the same. To prove it to you, MS Paint. I'm going to say O, images. Oh, MS Paint. Yes, that's demo. Thank you for catching that. Images, image number 2. Look, it's that same priceless picture that's out there of my daughter and I from years ago. So it's all good. Now, on my NTFS side of things, I'm going to run this lovely little program, and it's called corrupt disk for NTFS. And I'm going to say it is on the N drive. And it's going to go in and rewrite the data. You can probably tell when I run this utility to open up Paint, it doesn't work. I now have lost the picture. It's on a mirrored drive, and I still lost the picture to have access to it on that one guy. Over here, if I say corrupt file for ReFS on the O drive, same thing happens. Go up and choose MS Paint, the O drive. It found the better file from the other thing. That's a golf clap right there. That's... Whew. So that's about the best and most visual way that I can show you how our ReFS is different from a data integrity perspective of getting the good copy of the file out of the file system without on the fly, without the scrubber having to go off and to run to be able to do stuff for what it does. That demo came to me last night, literally at 11 o'clock after having dinner and a number of drinks for how to be able to do that. So scalability-wise, ReFS uses a highly scalable B-tree data for being able to store all of its data. That's how it can get the largest sizes of files and largest number of directories that are out there. File system abstractions are taking place at the exact same time with using key value tables also built on B-tree. Now, the neat thing is, capacity-wise, instead of having a generic allocation block for individual files, it chooses different allocation blocks as required when it's going off to protected systems, when it makes the writes to the disks. Make it so you're not wasting space, basically. It's a lot, you know how you have the wasted space that you used to have with NTFS? You don't have that. Oh, you know what? I forgot to show you this. And I'll switch back in just 1 second. If I say, see if this works. Okay, remember those 18 quintillion files? Check disk. That's NTFS. It's going. If I do the same thing, O drive, sorry, you don't need to run this. And it's still doing it on the other side. And that's only like an 8 gig drive. It's out there. So imagine that with 18 quintillion different entries that are out there. Application compatibility. The whole thing here that you need to be aware of is the fact that this is built on top of 20 years of NTFS. We didn't throw away the baby with the bathwater. For the most part, the bulk of the upper layer API is still the same, so your existing applications will probably still work just fine with the new ReFS environment that's out there. The stuff that's changed basically is down to lower levels. Some things you need to be aware of is that obviously it supports the bulk of the Win32 APIs. However, certain things will not work. You will not be able to have a DOS 622 machine map a drive to an ReFS share and get folder names. Sorry, does not support 8.3. NTFS-specific stuff doesn't do reparse indexes or MFT tables anymore. Does not support hard links or object IDs. And because there are certain things that are no longer required, like NTFS encryption, because you now have full volume encryption with BitLocker, they are not supported as well. One main thing I want to point out here that you should be aware of is the fact that you cannot do deduplication on an ReFS drive because of the way deduplication works. It's not supported with ReFS with this particular revision. So that's one thing to be aware of if you want to take advantage of dedupe inside NTFS version 4. NTFS. Very important to know that. Deployment-wise, it's extremely cost-efficient commodity hardware. Failover clustering gives you the better high availability capabilities. All the stuff I just did here is on a single system. It could be on a network system with a bunch of different access to stuff. It can be deployed. Another thing to be aware of, only available on Server 2012. The big part there also can only be deployed as a data volume. So you cannot have your system in boot partitions, anything but NTFS. Our EFS is for your data on top of that. It does not guarantee the absolute same level of compatibility. Basically just our little caveat warning to say, make sure you do your jurisprudence and do your testing. ReFS is a new file system, gives you the cost-effective stuff. That's marketing. You guys don't need to hear that again. It minimizes your CapEx. You guys definitely don't need to hear that again, but it is actually dirt cheap for the way you can do this because it works with any type of drive, SAS, USB 3, USB 2 on your individual workstations. This scales anywhere from the smallest tablet up to a 64-node cluster for what this does. Continuously available, highly scalable, absolutely fantastic. A couple of good resources for you in case you're interested. Virtualization of storage, scale and resiliency. There's a great white paper that's out there. How to configure this clustered storage space on Server 2012, and also some storage spaces facts. Very, very good stuff that's in there. There's some more resources. As they build, as they build, as they build. It's all good. And there is the reminder about evals. So I can take some questions now before you go. However, I will once again say, please be kind on evals. Fill them out. Speakers like to know how we did. Did you enjoy the session? And I do have time for questions, and I have at least 2 bottles of maple syrup up for those that ask good questions. Plus, to make it even more interesting, I have a little thing here that I was going to charge up and then fly into the audience, and whoever it hit, you got to have it, but then Nathan said I couldn't do that. So that's also available up and for some stuff. I'll take a couple of quick questions.